There is a number that astronomers have been passing between themselves, very quietly, for the last few years. It is not a large number by cosmic standards. It is not the age of the universe, or the distance to the farthest star, or the count of galaxies in the observable sky. It is smaller than any of those. It is, in fact, just a single digit followed by a decimal and two more digits. 14.3. A redshift of 14.3. If that means nothing to you yet, that is all right. It did not mean very much to most of us either, until recently. It is the kind of number that lives in technical papers and in the margins of conference slides. But behind it, pressed into those three small figures, is the light from a galaxy that should not, by our best understanding, exist. That is where we are going tonight, slowly, the way one walks toward a cliff in the dark, not to jump, but to sit at the edge and listen. If you find yourself here often at this hour, you can follow along quietly. There is a small button somewhere on your screen that keeps these nights coming back to you. I will not mention it again. The James Webb Space Telescope was never meant to break cosmology. That was not its job. Its job, as written in the mission documents, was more modest. It was to look further back in time than any instrument before it, to watch infrared light so stretched by the expansion of the universe that it had slipped out of the visible range, and to see, for the first time, the earliest galaxies, the first generation, the ones that formed when the cosmos was still young. And it did that. It began doing that almost immediately after it opened its segmented golden eye in the cold, quiet place 1.5 million kilometers from Earth, out at the second Lagrange point. Within months of first light, it was returning images of galaxies from when the universe was only a few 100 million years old. The trouble began almost at once.
The galaxies it found were too bright, too many of them, too massive, too organized. Some of them had already arranged themselves into disks. Some of them were already producing heavy elements that should not have existed yet, because the stars required to forge those elements had not yet had time to live and die. There is a way, in astronomy, of saying something is wrong without quite saying it. You say the observation is in tension with the model. You say the data exceeds the predictions of standard cosmology. You say a revision may be required. What you mean is, something does not add up. And something does not add up. Let me go backwards for a moment before we go forwards, because to understand why this is strange, you have to understand why we thought we already knew the story. For most of the last century, we have been assembling an account of how the universe came to look the way it does. It is one of the great pieces of work in human history, though it does not get spoken about in the same way as pyramids or symphonies. It is built out of mathematics and photographs and cold nights in high places, and it has a name that sounds almost plain: the Standard Model of Cosmology. Lambda Cold Dark Matter. That is what the letters stand for. In this account, the universe begins very hot, very dense, and expanding. It has been expanding ever since. Not into anything. That is one of the quiet difficulties of the theory that you have to sit with for a while before it stops bothering you. But simply expanding, space itself stretching, the distances between things lengthening as time moves forward. In the first few 100,000 years, there are no stars. There are no galaxies. There is only a fog of hydrogen and helium, glowing faintly with the heat of the earlier moments, slowly cooling. The universe during this period is opaque. Light cannot travel far before it runs into a particle and scatters.
If you were there, and you could not be, but if you were, you would see nothing. Only a soft, uniform glow in every direction. Then, at some point, The fog clears. The atoms settle. Light begins to move freely through the cosmos for the first time. And the universe enters a period that astronomers call, with a rare flash of poetry, the Dark Ages. The Dark Ages are exactly what they sound like. There is gas, but there are no sources of light, no stars, no galaxies, only the slow, quiet gathering of matter under gravity. Nothing to see. These Dark Ages last, according to our best models, for something like 100 million years, possibly 200. In that time, dense pockets of hydrogen collapse inward, heating as they collapse, until eventually the first stars ignite. These first stars are thought to be enormous, far larger than any star that exists in the universe today, and short-lived. They burn for a few million years and then explode, seeding the surrounding gas with the first heavy elements. From those remnants, the first galaxies begin to assemble. Small ones at first, dim, chaotic, irregular. They merge, they grow. Over hundreds of millions of years, they gather into the large, ordered structures we see around us now. That is the story. That is what we believed. It is a story of slow beginnings and gradual assembly, and it fit the data for a long time. The Hubble Space Telescope, Webb's predecessor, had pushed back the horizon of the observable universe further and further across 3 decades. It had found galaxies at redshifts of 7, 8, 9. Each one felt like a triumph. Light that had been traveling for more than 13 billion years, caught in a mirror a few meters wide above the atmosphere. These were the ancestors of our own galaxy. Faint smudges, mostly, ghostly, small. They fit. They fit the story of gradual assembly. They were small because the universe was young. They were faint because there had not yet been time for many stars to form. The picture held, and then Webb turned on. There is a moment I want to pause at, because I think it is the human heart of this. When the first deep field images came back from Webb in the summer of 2022, there was a period of perhaps 2 or 3 weeks during which the astronomical community did not quite know what to do with them. A team of people had spent decades of their lives preparing for a particular kind of result. They knew roughly what they expected to see. They had written the proposals. They had modeled the expected brightness and distribution of early galaxies. They had, in many cases, staked entire careers on certain predictions. And then the data arrived, and the data did not match. The galaxies were too bright. There were too many of them. They were too far away, and they should not have been that developed. And yet there they were, glowing in the infrared, pinpricks on a dark field. The first papers came out quickly, and they were cautious. Perhaps, the authors wrote, the redshift measurements were wrong. Perhaps these galaxies were closer than they appeared. Perhaps contamination from foreground sources was inflating their apparent brightness. Perhaps the models of early star formation needed only small adjustments. Over the following year and a half, many of those alternative explanations were tested, and most of them fell away. Spectroscopic follow-up, that is, the careful measurement of the precise wavelengths of light coming from these objects, which is the most reliable way to determine their distance, confirmed that many of the early candidates really were as far away as they appeared. They really were coming from the first few 100 million years of the universe. They really were, in some cases, too bright, too massive, too evolved for where they were in cosmic time. And then the redshifts kept climbing. 13, 13.2, 13.7, 14, 14.3. At a redshift of 14.3, the light from the galaxy has been traveling for approximately 13.5 billion years. The universe, at the moment that light was emitted, was less than 300 million years old. Less than 2% of its current age, barely past the end of the Dark Ages. In some models, not yet past them at all. And there, in that impossibly early moment, sits a galaxy, already formed, already making stars, already, in its small way, shining. I want to be careful here, because it is easy, in popular accounts of science, to collapse a complicated situation into a simple story of crisis. Astronomers have not, as a community, abandoned the standard model of cosmology. The model still works extraordinarily well in most of its domains. The cosmic microwave background, that faint glow left over from the early universe, which we can still detect today if we point the right instruments at empty sky, continues to match the model's predictions with exquisite precision. The large-scale distribution of galaxies continues to match. The abundances of light elements continue to match. But at the edges, something is happening. It is almost always at the edges that our pictures of the world begin to fail. That has been true throughout the history of science. The planets move, mostly, in circles, except for the small deviations that eventually overthrew the geocentric model. Newtonian gravity works beautifully, except for the slight precession of Mercury's orbit, which eventually required general relativity. The universe behaves, in the large, the way our equations say it should, except at the very earliest moments, where something we do not yet understand is producing more light and more structure than the equations predict. There is a particular galaxy that I want to name because it has come up often in these discussions, though I am going to describe it rather than fuss over the catalog identifier. It is a small, faint source, found in a deep field near the constellation Fornax. Its light comes to us from a time when the universe was roughly 300 million years old. That is young, very young, but in cosmic terms, it is also simply an early chapter in a long book. What makes this particular galaxy strange is not its distance, it is its chemistry. When astronomers took its spectrum, broke its light apart into its component wavelengths, the way a prism breaks sunlight into a rainbow, they found signatures of elements that were not supposed to be there yet. Oxygen, in particular. Oxygen has to be made inside stars, through the nuclear fusion of lighter elements, and then released into interstellar space when those stars die. To see oxygen in a galaxy that old means that an entire generation of stars had already lived and died before the galaxy emitted the light we are now receiving. That is a great deal of history compressed into a very short span of cosmic time. And this is not an isolated case. There are now dozens of galaxies in Webb's catalogs that share this pattern. Early, massive, chemically mature, too developed for their apparent age. This is what I mean when I say that something is happening at the edges. I am going to let that sit for a moment. There is a kind of quiet that comes at around 3 in the morning, if you are awake and the house is still, and the road outside has gone silent for long enough that you stop noticing it is silent. It is not the absence of sound, it is something closer to the presence of something else. An attentiveness, maybe. A listening. I think about that quiet sometimes when I read the papers coming out of Webb.
Because what we are doing as a species, when we point an infrared telescope at an empty patch of sky and hold it there for days on end, is something like that kind of listening. We are not speaking. We are not asking in any way the universe can hear. We are simply opening our eyes in the dark and waiting to see what returns. And what has returned
in the last few years is a set of photographs that do not quite fit the story we had been telling ourselves. Let me stay with the galaxies for a little longer, because the strangeness of what Webb has found is not just about their existence, it is about their shape. In the standard picture of galactic assembly, early galaxies are supposed to be messy, chaotic, irregular blobs of gas and young stars, still in the process of figuring out what they want to be. Spiral galaxies, the elegant pinwheels that define our mental image of what a galaxy looks like, are thought to take billions of years to form. They require a delicate balance of rotation, gravity, and star formation that can only be achieved after many generations of stellar birth and death have stirred the galactic material into stability. Webb has now found disk galaxies at redshifts well beyond what anyone had predicted. Galaxies with clearly defined rotation. Galaxies with bars. The straight, thick bands of stars that cut across the centers of many modern spirals, including our own Milky Way. These were not supposed to exist this early. Bars, especially, were thought to be late-stage features, requiring a mature and settled disk to form in the first place. And yet, there they are, photographed, measured, real. You can look at some of these images, if you ever want to. Many of them are public, available on the websites of the space agencies that run the telescope. They do not look, at first, like much. Most of them are small smudges of red-shifted light against a black background, a few pixels across.
You have to remind yourself, standing in front of the screen, what you are looking at. You are looking at a galaxy that existed almost 14 billion years ago, whose light has been traveling continuously toward this particular planet, in this particular corner of space, for nearly the entire history of the cosmos. And somehow it has arrived and struck a mirror and been recorded. That is not a small thing, even without the anomalies. But the anomalies are there, and they are accumulating, and they are beginning to reshape the questions we are asking. One of those questions is about dark matter. I want to approach this carefully because dark matter is one of those topics where it is very easy to slip into hype or into dismissal, and neither is honest. So I will say only what can be said plainly. We have, for about a century now, been aware that the gravitational behavior of galaxies does not match the visible mass inside them. Stars in the outer regions of galaxies orbit too quickly. Galaxy clusters hold together with more force than their luminous material should provide. Light from distant objects bends around intervening structures as if those structures contained far more mass than we can see. Again and again, in many different ways, the universe has told us that something is holding it together that we cannot directly observe. The standard name for that something is dark matter. It is not strictly matter in the sense that you and I are matter. It does not interact with light. It does not emit, absorb, or reflect. It is detected only by its gravity. It makes up, according to our best estimates, roughly 5 times as much of the universe's mass budget as ordinary matter does. In the standard model of cosmology, dark matter plays a crucial role in the formation of early galaxies. It is supposed to clump first, under gravity, forming invisible scaffolds called halos. Ordinary matter, hydrogen and helium gas, then falls into those halos, cools, and eventually forms stars. Without dark matter, the early universe would not have assembled itself quickly enough for galaxies to exist at all. One possible explanation for Webb's early massive galaxies is that dark matter clumped faster, or differently, than the models suggest. That the scaffolds were already more developed at earlier times than we had assumed.
This would not, in itself, break cosmology. It would revise a particular piece of it. Another possibility is that ordinary matter, the gas, was more efficient at forming stars in the early universe than it is today. That the first galaxies converted a larger fraction of their gas into stars and did so faster for reasons we do not yet understand. This, too, would be a revision rather than a revolution. A third possibility, more unsettling, is that our measurements of distance are subtly wrong. That the redshifts of these early galaxies do not mean quite what we think they mean. That the expansion history of the universe, which we infer from those redshifts, needs adjustment. And a fourth possibility, the one that tends to get the most attention, though I would say also the least support, is that the standard model itself is breaking down. That we have been wrong in some fundamental way about the early universe. The truth is that no one knows, at the time of this recording, which of these explanations will turn out to be correct. Possibly some combination of them, possibly something none of us have thought of yet. What we can say, with reasonable confidence, is that the picture we had 5 years ago is not going to be the picture we have 10 years from now. Something is shifting, slowly, carefully, in the manner of careful sciences, but shifting nonetheless. I find this comforting rather than troubling. I want to say why.
There is a temptation, when a field of science finds itself confronted with data it cannot explain, to treat that as a kind of defeat, a failure, a sign that we have been foolish. I do not think that is the right way to feel about it, and I do not think most of the astronomers involved feel that way about it either. A theory that cannot be broken is not a theory. It is a dogma. The value of a scientific model lies precisely in its vulnerability, in the fact that it can be tested and challenged and revised, and in some cases, overturned. When Webb returned images that did not fit the standard model, it was not a failure of science. It was science working exactly as it is supposed to. Instrument, observation, anomaly, revision. This is the oldest rhythm we have. And there is something else, something quieter, that I think about often in the hour before sleep. We live in a universe that is, as far as we can tell, about 14 billion years old. We have existed as a species, in the full anatomically modern sense, for perhaps 300,000 of those years. We have had astronomy in any recognizable form for a few thousand. We have had telescopes for 400. We have had infrared space telescopes for less than 50. And in that last 50 years, that brief flicker of attention, we have managed to see further in time and space than we had any right to expect. We have watched the light of the first galaxies arrive at our instruments. We have learned that our models are not quite right and begun the long work of figuring out why. We have, in effect, begun to take the measure of the entire visible universe from a small, wet planet orbiting an unremarkable star in the outer arm of one galaxy among trillions. That, to me, is the part that is worth sitting with. Not the anomaly itself, but the fact that we are in a position to notice it at all. It is very late now, where you are. I suspect that is why you are listening. There is a particular quality to the hours between 2 and 4 in the morning that makes certain thoughts easier and certain thoughts harder. The ordinary concerns of the day recede. The small self that moves through meetings and errands falls away. What remains is something older and slower. And that something is, I think, more receptive to the kind of material we are covering tonight. So let me bring it back to the galaxies. What Webb has found, in plain terms, is this. In the first few 100 million years after the Big Bang, in a period we once thought was dim and mostly empty, galaxies were already forming, already producing stars at rates that approach
or exceed the most vigorous star formation in the modern universe, already containing heavy elements that require prior generations of stars to produce, and already organizing themselves into structures, disks, bars, and in some cases, what look like central black holes, that we had not expected to see until much later. The early universe was not slow, it was not quiet, it was not a gradual assembly from nothing to something. Whatever processes governed the formation of the first galaxies, those processes were faster, more efficient, and more dramatic than the standard story suggested. Something was happening there, in that dark epoch we used to picture as empty, that we still do not understand. There is a particular category of object that I want to mention briefly, because it is where the strangeness intensifies. Webb has found, scattered through its deep fields, a set of objects that have come to be called, informally, little red dots. They are exactly what they sound like. Small, compact, very red sources of light, often unresolved, that is, appearing as single points rather than extended structures, and apparently located in the early universe. No one is entirely sure what they are.
The leading hypothesis, as I understand it, is that they are very young galaxies with supermassive black holes at their centers that are actively feeding. The red color comes partly from their high redshift and partly from dust that surrounds and obscures their central regions. If this interpretation is correct, then supermassive black holes, objects that can contain millions or billions of times the mass of our Sun, were already present in the universe when it was only a few 100 million years old. This is another thing that should not be possible under the old story. Supermassive black holes are supposed to form slowly, growing from smaller seeds over billions of years, accumulating mass through mergers and steady accretion of surrounding material. To find them already in place when the universe was so young means that either they formed very quickly from the beginning, perhaps directly collapsing from enormous clouds of gas without first becoming stars, or they grew far faster than our models allow. Either way, the picture shifts. I think about these little red dots sometimes when I cannot sleep. There is something haunting about them. Scattered across the sky, visible only to an instrument with a mirror larger and colder than any we had before, each one of them an entire galaxy, and at the center of each one, possibly, a thing so massive and so dark that light bends around it and cannot escape. Each one of them also unimaginably far away and unimaginably long ago, so that in a sense they are already gone. The galaxies those dots describe have spent the last 13 billion years evolving, merging, fading, becoming other things, and what we are seeing is only their earliest moment, preserved in light, delivered to us now. It is a peculiar kind of message, not intended for us, not meaningful to whatever existed then, which was not aware of us and could not have been. Simply light, released long ago, arriving tonight. I think about the distance that light has traveled. I think about the emptiness it has crossed. Most of the universe, after all, is empty. Not just the space between galaxies, which is vast, but the space between stars within galaxies. If you shrank our sun to the size of a grain of sand, the next nearest star would still be several kilometers away. The galaxy, seen at that scale, would be mostly darkness with a few scattered glittering specks. And the space between galaxies is emptier still, by many orders of magnitude. And through all of that emptiness, a few photons made it here, struck a mirror, caused a current, became a number, became, eventually, a small red dot on a screen
in a laboratory on a small blue planet whose surface is mostly water and whose atmosphere is mostly nitrogen. That chain of events, from the first stars, through the dark between galaxies, through the apparatus of the telescope, through the neurons of the astronomers who looked at the data, through the papers and the conferences and the slow spread of understanding, and eventually into these words, and into whatever room you are listening in, is not a small thing. It is, in fact, one of the things I find most difficult to look at directly for very long. I want to spend a little time now on the instrument itself, not on its technical details. Those are available in many places, written by people who know them better than I do, but on what it is, as an object in the world, and on what it means that it exists at all. The James Webb Space Telescope is, in a very literal sense, the largest and coldest mirror humans have ever placed in space. Its primary mirror is made of 18 hexagonal segments, coated in a thin layer of gold, and arranged into a shape that resembles a honeycomb about 6.5 meters across.
When it was launched at the end of 2021, it was folded up inside a rocket fairing because the mirror in its open form would not fit inside any rocket that currently exists. The unfolding, once the telescope was in space, took about 2 weeks. There were hundreds of individual mechanical steps, any one of which could have failed, and most of which had never been tested in their full working condition because the environment they required, vacuum, the cold of deep space, zero gravity, could not be reproduced on the ground. I remember watching the progress reports during those 2 weeks. A kind of held breath went through the entire astronomical community. Every day, another deployment, another tension boom extended, another mirror segment unfolded, another sunshield layer stretched into place. There was no margin for error. If any of it had failed, there would have been no way to fix it. Webb is too far from Earth to be reached by any crewed mission. Unlike Hubble, which orbits close enough for astronauts to service it, Webb sits at a point in space that is 4 times further away than the Moon, in a region where the gravitational pull of the Sun and the Earth combine to create a kind of stable orbital pocket. It is, in a very practical sense, unreachable, and it all worked. Step by step, over the course of those 2 weeks, the telescope unfolded itself, aligned its mirror segments to within nanometers of their intended positions, and cooled to its operating temperature of roughly 50 degrees above absolute zero. When it opened its eyes for the first time, in the spring of 2022, it saw the sky as no human instrument had ever seen it before. I think about this sometimes when I read the papers. The anomalies, the 2 bright galaxies, the strange chemistry, the compact red dots. All of these are the products of a machine that had to be folded up like origami, flung on top of a controlled explosion, unfolded in the dark, and cooled to a temperature that does not occur naturally anywhere on our planet. And behind that machine were tens of thousands of people. Engineers, scientists, administrators, technicians, machinists, contractors, the people who poured the concrete for the launch pad, the people who wrote the software that points the mirror, the people who designed the thin layers of aluminum in the sunshield, the people who argued in committee rooms for 30 years about whether the project was worth its cost. All of those people contributed, in ways large and small, to a single object now drifting in the cold outside the Earth's shadow, returning images of galaxies that existed when our solar system did not. This is not a small thing either. I mention it because it is easy, when we talk about cosmology, to lose track of the human weight of the instruments. It is easy to slip into the view that the discoveries simply arrived, as if they fell from the sky. They did not. They were earned, slowly, expensively, through the patient labor of a great many people,
most of whom will never be famous, and many of whom did not live long enough to see the results of their work. The original plans for what eventually became Webb date back to the late 1980s. Some of the scientists who drew the first sketches of its requirements are no longer alive. They did not get to see the deep field images. They did not get to read the papers about impossible early galaxies. They did their work and passed it on, and trusted that those who came after would complete it. There is something about that too that I want to sit with. The cosmos takes a long time to reveal itself, and the instruments we build to see it take a long time to be built.
A career's worth of effort might produce, in the end, a single improved measurement, a slightly sharper image, a refinement to an existing model. That is the nature of the work. It is not a field for people who need quick results. And yet, across many careers, across generations, the picture does change. The galaxies that Hubble could only hint at, Webb has now resolved. The questions that seemed beyond answering in the 1990s are now being answered, or at least being reshaped into better questions. The long, slow work continues. I find that, too, comforting. Not because it promises any particular outcome, but because it suggests a certain shape to human attention. We can, as a species, pay attention to something for a very long time. We can organize ourselves around a question that will not be fully answered within our own lives, and do the work anyway. That is not a common thing. Most of what we do for shorter horizons. Cosmology is one of the few fields where the timescales of the work begin to approach the timescales of the subject. Not closely. The universe is vastly older than our species, and our species is vastly older than our institutions, and our institutions are vastly older than any individual career. But still, closer than most. Let me come back to the galaxies for a while longer, because there are specific patterns in Webb's data that I have not yet described, and I think they are worth walking through slowly. The first is the sheer number of bright galaxies found at high redshift. In the first generation of Webb surveys, researchers were finding roughly 10 times as many luminous galaxies at redshifts above 10 as the standard models had predicted. Not twice as many, not 3 times, an order of magnitude more. This is a significant discrepancy. It is not the kind of number that can be waved away by invoking small adjustments to the models. Something more substantial is happening. Several explanations have been proposed. One is that the early universe produced a different kind of star than we see today. Stars much more massive, much hotter, much brighter, formed from primordial gas that contained no heavy elements and therefore cooled differently than modern gas does. Such stars, often called population 3, have long been predicted by theory but never directly observed. If they existed in the numbers and forms some theorists suggest, they could account for some of the excess light. Another explanation involves what astronomers call the stellar initial mass function, the distribution of masses among the stars that form in a given environment. In the modern universe, star formation tends to produce many small stars for every large one. But in the early universe, that balance may have been different. More massive stars per episode of star formation would mean more light per unit of gas converted, and could explain the brightness without requiring more total star formation. A third explanation is simply that early galaxies had less dust. Dust absorbs starlight and re-emits it at longer wavelengths, which effectively dims galaxies in the infrared bands Webb observes most sensitively. If the earliest galaxies had not yet built up significant dust, because they had not yet had time to produce and distribute the heavier elements from which dust is made, they might appear brighter than predictions based on more dust-rich environments would suggest. None of these explanations is mutually exclusive.
all of them may be partially correct. The full picture, when it eventually emerges, will probably draw on elements of several. The second pattern in the data involves what astronomers call the luminosity function, essentially a count of how many galaxies of different brightnesses exist at a given moment in cosmic time. Standard models predict that the luminosity function at high redshift should fall off steeply at the bright end, because there simply has not been enough time for very luminous galaxies to form. Webb's data suggests that this fall-off does not happen, or at least not as steeply as expected. There are more bright galaxies at high redshift than there should be. Not just a few, a statistically significant population. This, too, could mean several things. It could mean that some galaxies were forming stars in unusual bursts, briefly becoming very bright before settling into quieter phases. It could mean that black holes at the centers of early galaxies were contributing more light than previously assumed. It could mean that the fundamental process by which gas collapses into stars and galaxies was, in that early epoch, simply more efficient than it is today. The third pattern involves morphology, the shapes of the galaxies themselves. Webb has resolved many high redshift galaxies clearly enough to see structure within them. Not just points of light, but extended objects with identifiable features. And what it has found is that a substantial fraction of these early galaxies look, surprisingly, like scaled-down versions of modern galaxies. Disks, central bulges, spiral arms in some cases. The standard picture had suggested that early galaxies would look more like irregular blobs, the raw material from which modern galaxies would eventually be assembled through mergers and gradual settling. Webb has found that assembly happened, in many cases, remarkably fast. Galaxies that formed within the first billion years of cosmic history often appear, at least in silhouette, not unlike galaxies that exist today. This does not mean the universe was boring in its early phases. Far from it. There are genuinely strange objects in Webb's catalogs. Galaxies with odd chemical signatures. Galaxies that seem to be in the middle of violent merger events. Galaxies whose central black holes appear to be disproportionately massive compared to the galaxies themselves. Plenty of strangeness. But the overall pattern is one of earlier maturity than expected, not of chaotic prolonged adolescence. Something about the early universe was in a hurry. There is a related question that I find myself returning to, and it is the question of reionization. This is a piece of cosmological history that does not get much attention outside the field, partly because its name is cumbersome, and partly because it happens in a period that, from the outside, looks like not much is going on. But it matters here, because Webb's findings are directly reshaping our understanding of it. To understand reionization, you have to remember where we left the universe in the earlier part of this recording. After the Dark Ages ended, after the first stars ignited, and the first galaxies began to assemble, the cosmos was still full of neutral hydrogen. That is, hydrogen atoms with their electrons bound in place, drifting through intergalactic space. This neutral hydrogen is opaque to certain wavelengths of light. It absorbs ultraviolet photons very efficiently. If you were to try to see through a thick fog of neutral hydrogen with an ultraviolet detector, you would see almost nothing. For a long time, the early universe was full of this fog. Stars were burning, galaxies were forming, but between them stretched vast regions of neutral gas that light could not easily cross. Then, over some period of hundreds of millions of years, the fog lifted. The neutral hydrogen was ionized, its electrons stripped away by the ultraviolet light from the first galaxies and the first black holes. The universe became transparent again to those wavelengths for the first time since the earliest moments after the Big Bang. This process, the gradual ionization of the intergalactic medium by the light from the first luminous sources, is called reionization. It is the transition that took the universe from the dark ages into the lit-up cosmos we live in now. The question that has occupied cosmologists for decades is this: what exactly provided the ultraviolet light that drove reionization? Was it mostly the first stars? Mostly the first black holes feeding on surrounding gas? Some combination? And was the light provided steadily, or in bursts, or in some other pattern? Until Webb, we had only indirect evidence. We knew, from observations of the cosmic microwave background and from the spectra of distant quasars, that reionization was substantially complete by about 1 billion years after the Big Bang. We knew it must have begun earlier than that, but how much earlier was genuinely uncertain. Webb is now letting us see the sources of light during reionization directly. It is letting us measure how many early galaxies there were, how bright they were, and, crucially, how much of their ultraviolet light actually escaped their galaxies to ionize the surrounding intergalactic medium. That last number, called the escape fraction, turns out to be harder to measure than anyone had expected, because most of the ultraviolet light produced inside a galaxy is absorbed by the gas in the galaxy itself before it can escape. The current picture, based on Webb's first few years of observations, is that early galaxies were more numerous and brighter than earlier models had assumed. This means they were probably contributing more ultraviolet light to reionization than we thought. Whether they were contributing enough light on their own to drive the whole process, or whether early black holes must have played a significant supplementary role, is still being worked out.
I mention all of this because it is an example of how cosmology actually progresses.
Not in great dramatic revolutions usually, but in slow adjustments to well-posed questions. The question, what drove reionization, has been asked for decades. The answer is gradually coming into focus. It is not a simple answer. It involves populations of galaxies, properties of their stars, physics of how light escapes from gas, and the timing of black hole formation. But the pieces are falling into place, one observation at a time. And each time a piece falls into place, other pieces come loose. The early galaxies are more luminous than expected, which helps explain reionization, but also requires that we rethink early star formation. The early black holes are larger than expected, which complicates our models of how black holes grow, but may help explain the detailed structure of reionization. Every answer spawns new questions. This is not frustration. This is the shape of the work. Let me step away from the technical details for a little while now, because I want to speak more gently. There is a thing that happens when you read a great deal of astronomy that I have come to think of as the quiet vertigo. It is not fear. It is not exactly awe either, though it shares something with awe. It is the slow dawning sense that the scales involved, of space, of time, of number, are beyond the reach of ordinary intuition, and that the mind, when it tries to grasp them, does not quite succeed, but does not quite fail either. It hovers at the edge of comprehension, aware that something very large is present, without being able to hold the whole of it. I think most people who spend time with these subjects know the feeling. It tends to come at unexpected moments. You are reading a paper about a particular galaxy. You are looking at a graph of luminosity versus redshift.
You are standing outside at night, or lying awake in a dark room, and you remember that the starlight you are absorbing, or would be absorbing if the ceiling were gone, has been traveling for years, or centuries, or millennia, or in some cases most of the age of the cosmos.
And then, for a moment, the ordinary world thins. The walls of your room, the weight of your body, the noise of the street outside, all of it becomes less solid. You become aware that you are, in a literal sense, hanging in space, on the surface of a small rotating planet, in the outer regions of a mid-sized galaxy, in a volume of the universe that extends in every direction beyond what any instrument will ever be able to measure. And then the feeling passes. The walls of your room return. The weight of your body returns. You get up, or you do not, and the world continues to insist on itself. I have learned over the years not to try to hold on to that feeling when it comes. It does not respond well to grasping. It is, in some way, more like a slow tide than an event. You can be aware of it and let it move through you, and then you can return to ordinary attention. Forcing it to stay, or trying to build a permanent philosophy on its foundation, tends to produce something brittle. But I have also learned that these moments are not nothing. They are not simply neurological quirks to be dismissed. They are, I think, an accurate perception of a fact that our ordinary cognition is not built to hold. The cosmos really is that large. We really are that small. The feeling, when it comes, is not a distortion. It is a partial glimpse of a truth we usually look away from. And the reason we look away from it, I believe, is not that it is frightening, though it can be, but that it is simply too much to sustain. The ordinary business of being alive, of eating and working, and loving and sleeping, requires a smaller scale of attention. You cannot run a kitchen while holding the full weight of cosmology in your mind. You cannot raise a child while looking, unbroken, at the distances Webb is measuring. The mind chooses, sensibly, to live most of its hours on a human scale. But sometimes, at night, when the small business of the day has been laid aside, sometimes, at the kind of hour when you might be listening to something like this, the mind relaxes its grip on the human scale and lets the larger scale seep in. That is, I think, what these recordings are for. Not to teach, primarily, not to impress, not even to help you sleep, though that is one of their functions. They are, I think, a way of giving the mind permission to loosen, to acknowledge the larger scale for a little while, without having to do anything about it, to rest in the fact of the cosmos, rather than being overwhelmed by it. The cosmos does not require your attention. It does not require your understanding. It will continue doing what it does whether or not anyone is watching. But if you want, for a while, to let your attention drift in that direction, if you want to feel, for the duration of a single recording, the weight and depth of what is out there, that is something you are allowed to do. It is one of the small gifts that consciousness permits. I want to return to the early galaxies, but along a different path this time. There is a concept in astronomy called cosmic dawn. It refers, loosely, to the period during which the first stars and galaxies began to light up the universe, the transition from the Dark Ages into the era of visible structure. The phrase is evocative for a reason. It really does describe something like a dawn, though at a scale of hundreds of millions of years rather than hours. Before cosmic dawn, the universe was dark in a way that is difficult to picture. Not dark in the sense of a nighttime with stars. Dark in the sense of no sources of visible or ultraviolet light at all, anywhere.
Only the dim residual heat of the earlier moments, the cosmic microwave background, filling space uniformly at temperatures too low to be seen by any eye. And then, somewhere in that darkness, the first star lit. We do not know where, we do not know when exactly,
though we can estimate the era. We do not know what it looked like, though we have models. What we know is that at some particular moment, in some particular region of collapsing gas, the density and temperature crossed a threshold, and fusion began, and a point of light appeared in a universe that had, until that moment, contained no points of light at all. I think about that first star sometimes. Not because it matters exactly. The universe contained, almost immediately thereafter, an enormous number of stars, but because of the mental image it provides. A single light in a sea of darkness, with no observer to see it, no eyes yet existed, no brains to interpret, no instruments, just the light itself, beginning, and the dark around it, and the slow unfolding of physics. That star died quickly. The first generation of stars were massive and short-lived, burning through their fuel in a few million years, and then collapsing or exploding. But in their brief lives, they began the long process of cooking the raw hydrogen and helium of the early universe into heavier elements: carbon, oxygen, iron, the elements we are made of. Every atom of carbon in your body passed through the core of at least one star before it reached you. Every atom of iron was forged in the final moments of a massive star's life, in an explosion powerful enough to outshine an entire galaxy for a few weeks. This is not metaphor, it is literal chemistry. You are, in a direct causal sense, a descendant of those first stars. And the Galaxies Webb is now photographing, the impossible early ones, the too bright ones, the ones with already formed disks and already present heavy elements. Those galaxies are closer to that first moment than anything we have ever seen. Not as close as we would like, probably. The very first stars themselves, the population 3 stars I mentioned earlier, remain beyond direct observation. Their light is too faint and too far away, even for Webb. But the first galaxies, the ones that contained many such stars, are now within reach. We are, in effect, looking at the dawn itself. Not the instant of sunrise, but the gradual spreading of light across a sky that had been empty of light since the beginning. And we are finding that this dawn happened faster than we thought, that the sky filled with galaxies more quickly than our models predicted, that the light came on sooner and brighter and in greater abundance than we had imagined. That changes the shape of the story. It does not change the ending. The universe still looks today the way it looks, but it changes the beginning, and the beginning matters. The beginning determines how the rest unfolds. There is a chance, of course, that the revision will be small, that a few adjustments to the standard model will accommodate all of Webb's findings without requiring anything more dramatic. This is, historically, what usually happens. Most anomalies in physics turn out to be refinements rather than revolutions. But there is also a chance, small but not negligible, that something more fundamental is being revealed, that the early universe contained processes or constituents that our current models do not include, that the first 100 million years, which we thought we understood in broad outline, are in fact the site of physics we have not yet begun to describe. We will not know for a while. The data keeps accumulating, the models keep adjusting, the papers keep arriving.
And somewhere in the next few decades, if the instruments keep looking, a clearer picture will emerge. I will probably not be the one to explain that picture. These recordings are a snapshot of a particular moment, this moment, tonight, when the question is still open. When Webb has shown us something strange, and we have not yet fully figured out what it means. If you return to this recording in 10 years, it will be a historical document. The mystery will have resolved, or deepened, or been replaced by some other mystery that has not yet presented itself.
That is the nature of the work. Each era in astronomy has its open questions, and each generation of astronomers inherits the questions of the previous generation while generating new ones of their own. Right now, the open question is cosmic dawn. Right now, we are in the middle of an unexpected revision to our understanding of the early universe. It is a good time to be listening. Let me slow down even more now. We are past the middle of this recording, and the latter portion should feel slower than the earlier portion, the way a long conversation naturally slows as the night deepens. There is a window in the room where I write these scripts that looks out over water. Not the ocean, a smaller body of water, a kind of inlet that goes quiet at night. On the far side of the inlet, perhaps 2 kilometers away as the crow flies, there are houses. Most of them are dark at the hours I work. One of them, however, has a single light that stays on all night, in a window on the upper floor. I do not know why that light is on. I have never met the person who keeps it lit. I think, sometimes, that they cannot sleep either, that they work at night, as I do, that they have a child who needs a nightlight, or an illness, or simply a preference for the comfort of a single lamp in a dark house. I will probably never know, but the light is there, every night, across the water. And every night, when I look up from the writing and let my eyes adjust to the dark, it is one of the first things I see. I mention this because it has become, without my quite intending it, a small fixed point in my nights. An anchor. The light is on. Someone else is awake. The world has not emptied itself entirely. There are probably similar fixed points in your nights. A streetlight that always burns outside your window. A neighbor whose kitchen stays lit until very late. A ship that passes along a particular coast at a particular hour. We all find these small, steady things, I think, when we spend time awake in the dark. They become, in some way, more meaningful than they have any right to be. And I think, this is a stretch, but I think it is a reasonable stretch, that the light from those distant early galaxies works, at a different scale, as a similar kind of steady presence. It has been traveling toward us for almost the entire history of time. It has not stopped. It has not wavered. It has crossed unimaginable distances, passed through unimaginable emptiness, and continues to arrive every moment in infrared bands that Webb is carefully tuned to catch. It is a steady thing. Not in the sense that it is unchanging. Individual photons come and go. Individual galaxies evolve and dim and merge. But in the sense that the overall flow has continued for as long as the universe has been lit. There has not been a moment since cosmic dawn when light from distant galaxies was not arriving somewhere in space. Most of it arrives in places where no instrument is there to catch it. Most of it simply passes through and continues on, and eventually encounters something else, or never encounters anything, and spreads outward forever. But some small fraction of it arrives here, on this planet, at this telescope, tonight. That is a steady thing too. The lamp across the water, and the light from the early galaxies. Both of them, in their very different ways, are steady against the larger dark. I find that comforting. There is one more aspect of Webb's findings that I have not yet described, and I think it belongs here, in the slower latter half of this recording. It has to do with what astronomers call the cosmic distance ladder. The phrase is not poetic, but the concept is important. The cosmic distance ladder is the chain of methods by which astronomers determine how far away things are. Each rung of the ladder depends on the rung below it. Nearby distances are measured directly by a method called parallax, essentially watching how the position of a nearby star shifts against the background of more distant stars as the Earth moves around the Sun. Once you know the distances to nearby stars, you can calibrate other methods. The brightness of certain types of variable stars, for instance, or the brightness of certain types of supernova, and use those methods to measure distances further out. And so on, rung by rung, until you reach the most distant galaxies. The highest rungs of the ladder, the ones Webb is now pushing into, depend ultimately on the rungs below them, which means that if there is an error anywhere in the chain, it propagates upward. A small miscalibration in the nearby rungs becomes a larger uncertainty in the far rungs. And for some time now, there has been an unresolved tension in the cosmic distance ladder that has been bothering cosmologists. It is called the Hubble tension. The name comes from the fact that it involves the Hubble constant, the number that describes how fast the universe is currently expanding. Different methods of measuring this constant give slightly different values. When astronomers use the cosmic microwave background, along with the standard model of cosmology, to predict the expansion rate, they get one number.
When they use the cosmic distance ladder, measuring nearby objects and working outward, they get a slightly higher number. The two values disagree by an amount that is small in absolute terms, but that is too large to be dismissed as measurement error. This disagreement has been deepening, not resolving, over the last decade. As measurement techniques have improved, the two values have become more precise without becoming more consistent. Each of them is now known to within a couple of percent, but they are genuinely different. Something is wrong somewhere, either in one of the measurement chains or in the underlying cosmological model that connects them. Webb is not, on its own, going to resolve the Hubble tension. That is not its primary purpose, and its observations alone are not sufficient to settle the question. But Webb is contributing data that bears on the problem. Its observations of variable stars in nearby galaxies are helping to refine the lower rungs of the distance ladder. Its observations of distant galaxies are testing whether the standard model's predictions about early cosmic evolution remain consistent with what the microwave background tells us. What the community is slowly converging on, and I want to be careful here because opinions genuinely differ, is the sense that the Hubble tension may not be going away. It may be pointing to something real, some aspect of the universe or of our models that we have not yet correctly characterized. I mention this because it connects, in an indirect way, to the early galaxy anomalies. If the early universe was evolving differently than our models predict, if dark matter was clumping differently, or if ordinary matter was forming stars more efficiently, or if some new physics was playing a role, then those differences could plausibly affect the expansion history of the universe in ways that would show up as a tension in the Hubble constant. Or they might not. The connection is not proven. Many cosmologists are skeptical that the two anomalies are related, but the fact that both of them exist at roughly the same time in the same broad field of cosmology is itself interesting. It may be that we are living through a period when multiple small inconsistencies are quietly accumulating, none of them individually dramatic enough to force a revision, but all of them together pointing in the same vague direction. Historically, this is often how paradigm shifts begin, not with a single dramatic discovery, but with a slow buildup of small discrepancies that eventually become too large to ignore. We may be at the beginning of such a buildup. We may not. It will take years, perhaps decades, to know. In the meantime, the work continues. Webb keeps looking, other instruments keep measuring, theorists keep proposing. Every paper adds a small piece of evidence,
and every conference reshapes the collective understanding by a small increment. And slowly, across the effort of many people over many years, the picture changes. This is how we learn things about the universe. Not quickly, not dramatically, but persistently, across generations, in the slow accumulating way that, over enough time, produces genuine knowledge. I want to speak, for a little while, about the scale of what Webb does not see. I have talked a great deal about what the telescope has found. The early galaxies, the little red dots, the unexpected chemistry, the surprising shapes. All of these are real observations of real objects, but they represent, in the end, a very small fraction of the universe. The observable universe, the region from which light has had time to reach us, is enormous. Its radius is about 46 billion light-years. Its volume, if you wanted to estimate it, contains something like 2 trillion galaxies. Each of those galaxies contains, on average, hundreds of billions of stars. The total number of stars in the observable universe is a number with so many zeros in it that writing it out serves no practical purpose. Webb has observed so far perhaps a few 100,000 galaxies in detail, a few million more in various survey programs in less detail. This is a tiny fraction of the total. If you imagine the observable universe as a very large ocean, Webb has, in effect, examined a few buckets of water. And beyond the observable universe, there is more. How much more, we do not know. The universe may be finite, but much larger than what we can see. It may be infinite. Our equations do not uniquely determine the answer, and our observations do not reach far enough to settle the question. If the universe is infinite, and this is a genuine possibility, not a fringe view, then everything we can ever learn about it, through all the telescopes we will ever build, across all the centuries of astronomy that lie ahead of us, will still be a vanishingly small fraction of the whole. We will always be working with local samples of something that, in the large, exceeds us by an amount that has no meaningful upper bound. This is not defeatism. It is simply a fact about the situation we are in. The universe is larger than we can survey. Our knowledge of it will always be partial. And yet, and this is the part I find remarkable, we can still learn real things. We can still measure and predict and model and gradually refine our understanding. The largeness of the universe does not prevent us from knowing anything about it. It only prevents us from knowing everything. That distinction is important. Between knowing nothing and knowing everything lies an enormous range, and within that range is where all of science lives. We are not trying to know everything. We are trying to know more than we knew yesterday.
That is a much more modest goal, and a much more achievable one. And it turns out, in practice, to be sufficient for a great deal of real progress. Webb is one more step along that path. Not the final step, not a decisive step, just another step, carefully placed, in a long walk that began with the first humans who looked up at the stars and began to wonder. I do not know how long that walk will continue. None of us does. The species may survive for another 1,000,000 years, or it may not. The instruments may keep improving, or we may enter a period when we build fewer of them. The knowledge accumulated so far may be carefully preserved and expanded upon, or it may be partially lost and have to be rediscovered. These are not idle concerns. There have been, in the history of our species, periods when knowledge was lost. Libraries have burned. Languages have died. Whole traditions of inquiry have collapsed and had to be rebuilt, sometimes centuries later, from fragments. There is no guarantee that the knowledge we are accumulating now will persist. There is no law that says the curve of human understanding must continue upward. But as of tonight, the curve is still moving upward. As of tonight, the instruments are still looking. As of tonight, the papers are still being written, and the models are still being refined. And somewhere, in some astronomy department, a young researcher is looking at a spectrum that does not quite make sense, and is beginning the slow work of figuring out why. That is enough. That is enough for tonight. I want to say one more thing about scale, and then I will let this recording descend toward its ending. The scale of time that cosmology works with is not a human scale. No one can really imagine 13 billion years. The mind stops somewhere short of that, somewhere around 1 million perhaps, if it is well practiced. Beyond that, the numbers become symbols that the mind manipulates without fully grasping. This can feel, sometimes, like a failure, as if we ought to be able to imagine these spans if we really tried, and our inability to do so is a kind of inadequacy. I do not think it is. The mind is not built for those scales, and there is no reason it should be. The scales of evolution, of geology, of cosmology, these are not the scales at which our ancestors lived. Our ancestors lived at the scale of seasons, of generations, of lifetimes. That is what our cognition is tuned to. Expecting the mind to intuitively grasp 13 billion years is like expecting the ear to hear radio waves. It is simply not the instrument for the job. But we have built other instruments. We have built mathematics. We have built the symbolic language of numbers and equations, which lets us calculate and compare across scales that our intuition cannot touch. We have built telescopes and spectrographs and detectors, which let us see what our eyes were not built to see. We have built cooperation, institutions, archives, peer review, the whole slow machinery of science, which lets us pool the partial observations of many individuals into something larger than any of us could produce alone. These are not extensions of our senses exactly. They are something else. They are prosthetics of attention. They let us attend to things that our native cognition cannot attend to. Webb is one of these prosthetics. A very expensive, very carefully engineered prosthetic of attention, floating in the cold at the second Lagrange point, paying attention on our behalf. It looks where we cannot look. It sees what we cannot see. It returns, to us, a version of the universe that our eyes would never have shown us. And when we look at its data, when we read the papers, or gaze at the images, or hear about them in recordings like this one, we are, in a certain sense, borrowing its attention. We are letting the telescope attend on our behalf. The mind cannot reach 13 billion years on its own. But the telescope can. And the telescope reports back. That is the trick of it. That is how we know anything at all about the early universe. Not because our cognition stretches that far, but because we have built something that does, and then we have learned to trust what it tells us after checking it carefully. I find that, too, quietly remarkable, that we have, as a species, figured out how to outsource attention to machines, how to know things we cannot personally witness, how to trust evidence we did not directly collect. This is not a trivial achievement. Many cultures across many centuries have not fully developed this capacity, or have developed it and then lost it. We happen to live in a period when it is highly developed, and the fruits of that development include, among many other things, a set of photographs of galaxies that existed before our solar system existed. That is a strange and valuable inheritance. There is something I have been circling around, and I want to name it now, quietly, before we go further. The word is indifference. The universe, as far as we can tell, does not know that we are here. It does not arrange itself in our favor. It did not, when it formed its first galaxies in those strange early millions of years, have any awareness of the creatures who would one day build instruments to observe it. The processes that shaped the early cosmos, whatever they were, whatever we are still learning, were not aimed at us. They were not aimed at anything. They simply happened, following the rules of physics, in a volume of space so large that the word large begins to lose its usefulness. Many people find this difficult. I understand why. There is a particular kind of loneliness that comes with the realization that the stars are not arranged for us, that the cosmos does not notice us, that whatever meaning our lives have is a meaning we bring with us, and not one we discover written in the sky. I want to say, very carefully, that I do not find this loneliness. I find something else, and I think that something else is part of why I write these scripts, and part of why you might be listening to them at this hour. If the universe were arranged for us, we would have obligations to it. We would have to live up to whatever purpose was intended. We would have to decipher a plan, align ourselves to it, worry that we were falling short of it. The indifference of the cosmos is, in a sense, a release from all of that. It does not require anything of us. It does not judge us. It does not watch. What we do with our brief time here is, then, entirely our own affair. That is what I mean when I say that indifference is a form of freedom. Now, back to the edge. The edge of the universe is not a wall. This is something worth saying slowly, because most of us carry, somewhere in the back of our minds, the idea that the universe must have an edge the way a room has walls. That if you traveled far enough in one direction, you would eventually hit something. This picture, however natural it feels, is not correct. What we call the edge of the observable universe is simply the distance beyond which light has not yet had time to reach us. The universe is about 14 billion years old. Light, for all its speed, has had only that long to travel. So anything farther than about 46 billion light-years away, a number that is larger than 14 billion light-years, because space has been expanding while the light was traveling, cannot yet be seen. It may be out there. Almost certainly something is out there, but its light has not arrived. This means that when Webb looks at a redshift of 14.3, it is not looking at the edge of the universe in the sense of an outer boundary. It is looking at the edge of what we can, in principle, see. It is looking as far back in time as the current age of the cosmos allows. And beyond that edge, there is more. More galaxies, presumably. More distance. Possibly, though we do not know, more universe entirely, in forms we cannot observe from where we are standing. There are speculative ideas about what lies beyond. Some physicists have proposed that our universe is one of many, arranged in ways that are hard to describe and harder to test. Some have proposed that the very earliest moments of our own universe involved physics we do not yet have the equations for. Some have proposed that the apparent anomalies Webb is finding are hints of something much larger, A revision not only to our model of galaxy formation, but to our model of the very beginning. I will not spend long on these because they are hypotheses, and because the honest answer to most of the deepest questions is that we do not yet know. We do not know why the early universe produced galaxies faster than our models predict. We do not know what dark matter actually is. We do not know what happened in the first fraction of a second after the Big Bang, when the density of the cosmos was so extreme that our current theories cannot describe it. We do not know whether the universe will expand forever, or slow, or tear itself apart in a distant future. These are not small gaps. They are not the sort of gaps that can be filled with a few more observations. And yet the instruments keep looking. The papers keep arriving. The models keep refining. In a century or two, if our species holds together that long, a future listener will look back at this period of confusion the way we look back at the confusion of pre-Copernican astronomy, as a moment when the picture was visibly failing and the next picture had not yet arrived. We are, in other words, living in a transitional moment in cosmology. Not a revolutionary one, necessarily, not yet, but a moment of genuine uncertainty about the very earliest chapters of the story. A moment when a telescope 1.5 million kilometers from Earth has returned images we did not expect. And the people who study those images are quietly revising what they thought they knew. I find that remarkable. I find it quietly thrilling, in the slow way that suits this hour. Let me slow down a little more now. There is a thing I have noticed, over the years, about the kind of listener who finds these recordings. You are usually alone, often awake later than you intended, often thinking, before you found this recording, about something that had been weighing on you. A decision, a loss, a future, a past. I do not know what brought you here tonight. I will not pretend to. But I think that part of the reason these stories about the cosmos are useful at this hour is that they shift the scale. When the mind has been turning in small circles for a long time, caught on something close and personal and unresolved, it can help, sometimes, to step back. Not to dismiss the thing that is troubling you, that rarely works and it is not my intent, but simply to place it, for a moment, against a larger background. To remember that the very atoms in your body were forged inside stars that died billions of years before the Earth existed. To remember that the light-reaching Webb tonight began its journey before any creature on this planet had words. To remember that you are not separate from the cosmos. You are one of the ways it has come to look at itself. That last phrase is not mine. A number of people have said versions of it across the decades. But it is true, I think, in a way that goes beyond the poetry of it. The hydrogen in your blood, the calcium in your bones, the oxygen you are breathing, all of it came from stars. The iron in your hemoglobin was forged in the core of a massive star that exploded, at least once, before our sun was born. You are made of the same material as those early galaxies Webb has been photographing. The same material. And that material, here, in you, has done something the material in those distant galaxies has not yet been observed to do. It has assembled itself into a form that can wonder, that can lie awake at 3 a.m. and think about things that happened 13 billion years ago, that can listen quietly in the dark to a voice talking about redshift and dark matter and the strangeness of the early universe, and feel for a moment that it understands. Whether that is a rare thing in the cosmos or a common thing, we do not know. We have not yet found other examples. We have been looking, not very hard and not for very long, but we have been looking. And so far, we have found only silence. That silence may mean many things.
It may mean that we are alone. It may mean that we have not looked carefully enough, or in the right way, or for long enough. It may mean that the universe is full of listeners, all of them as uncertain as we are, each of them pointed in the wrong direction. I do not know. Neither does anyone. What I do know is that tonight, on this particular evening, in your particular room, wherever you are, some small portion of the cosmos is aware of itself. It is thinking about things that happened before it existed. It is trying to fit an image of the universe into a mind that evolved for much more local concerns. That, to me, is the quietest miracle of what Webb has shown us. Not the anomaly, not the too bright galaxies, or the too early black holes, or the unsettled cosmology. Those are important, and astronomers will be arguing about them for a long time. But the deeper thing, the thing I find myself thinking about in the hour before I finally sleep, is simpler. We are here. We can see. The light arrives, and we receive it, and in receiving it we become, briefly, something more than the small biological animals we otherwise are. We become witnesses. The universe does not require witnesses. It did not in its long, dark, early epochs have any.
It would be, without us, exactly what it is.
The galaxies would still form. The light would still travel. The edge of the observable region would still recede, slowly, into deeper time. But for a little while now, on this one planet, there are witnesses. And some of those witnesses have built mirrors and pointed them at the oldest light they can find and carried back images of a universe that does not quite behave the way they expected. If you take anything from tonight, I hope it is this. You are not separate from any of it. The same physics that shaped those distant early galaxies shaped you. The same hydrogen that fell into the first halos is, right now, moving through the water in your body. The same time that has been passing for the universe has been passing for you, in a much smaller quantity, in exactly the same direction. And the fact that we are, any of us, in a position to notice this, the fact that the same matter that has spent 14 billion years mostly drifting in the dark has, in at least one small corner, begun to look up, that is not a small thing. That is not a small thing at all. Somewhere very far away, in a direction we can point to but not travel, there is a galaxy whose light has been on its way to us for almost the entire history of time. That light left before our planet formed. It left before our sun formed. It left when the universe was young and strange and producing structures we do not yet understand. It has crossed unimaginable distances. It has passed through the outskirts of countless other galaxies. It has been bent slightly by intervening mass. It has stretched with the expansion of space until what was once ultraviolet became visible, and what was once visible became infrared, and what was once infrared became longer still. And tonight, or last night, or some night very recently, a few of those photons completed their journey. They struck a mirror at the second Lagrange point. They generated a current.
They became data. They became, eventually, a paper and a headline, and then a quiet conversation in the dark between a narrator you have never met and a listener he will never see. Far away, through the window of the house where these scripts are written, there is a single light that stays on all night in the house across the water. I do not know who lives there. I have never met them. I imagine, sometimes, that they are also awake, that they are also listening to something. That light is very small. It is also, in its own way, one of the things the universe has produced. Somewhere out there, at the edge of what we can see, a galaxy is still shining the way it shone 13.5 billion years ago. And here, much closer, a lamp is on. And here, closer still, you are awake. Rest now, if you can. The universe will keep doing what it does. And in the morning, or whenever morning comes, it will all still be there. Good night.